Hey everyone, welcome. Today we're looking at Leetcode problem 2176, called Count Equal and Divisible Pairs in an Array. Sounds a bit mathematical maybe, but don't worry, we'll break it down together, step by step. It's actually quite straightforward once you see the pattern. Ready? Let's dive in. Okay, so here's the official problem description. Essentially, we're given a list of numbers, called and successor than another number. Our job is to find out how many pairs of positions, let's call them, and exist in the list that satisfy three conditions. First, the position must come before position. Second, the numbers at these positions, nums and nums, must be exactly the same. And third, if you multiply the position numbers and together, the result must be perfectly divisible by. We just need to count how many such pairs we can find. The constraints tell us the list isn't too huge, maybe up to 100 numbers. Got the basic idea? Let's walk through this example. Our list is 3, 1, 2, 2, 2, 1, 3, and our k is 2. We need pairs, ij, where I less than j, the numbers are equal, and ij is divisible by 2. Okay, let's look for pairs. How about the first and last number? They are both 3. The positions are 0 and 6. Is 0 less than 6? Yes. Are the numbers equal? Yes. Both 3. Is 0, 6 equals 0 divisible by 2? Yep, 0 is divisible by anything. So that's one pair, 0, 6. What about the number 2? It appears at positions 2, 3, and 4. Let's check pair, 2, 3. Is 2 less than 3? Yes. Is nums 2 equal to nums 3? Yes, both 2. Is 2, 3 equals 6 divisible by 2? Yes. That's our second pair, 2, 3. Now pair, 2, 4. Is 2 less than 4? Yes. Are nums 2 and nums 4 equal? Yes. Both 2. Is 2, 4 equals 8 divisible by 2? Yes. Third pair, 2, 4. How about pair, 3, 4? Is 3 less than 4? Yes. Are nums 3 and nums 4 equal? Yes. Both 2. Is 3, 4 equals 12 divisible by 2? Yes. Fourth pair, 3, 4. Are there any other pairs? There's a 1 at position 1 and position 5. Let's check. 1, 5. 1 less than 5? Yes. Nums equals nums? 5. Yes. Both 1. Is 1, 5 equals 5 divisible by 2? No, it's not. So this pair doesn't count. Looks like we found 4 pairs in total. Makes sense. So how can we approach this systematically? The most direct way, often called the method, is usually the first thing to try. We basically need to examine every possible pair of indices, I quote use j, that meets the first condition, which is that I must come before j. For every single one of those pairs, we then just check the other two conditions we talked about. Are the numbers in the list at those spots identical? And is the product of the spot numbers I and j divisible by k? If both checks pass, we just add 1 to a running counter. After checking all possible pairs, that counter will hold our final answer. Seems straightforward enough, right? Alright, here's the Python code for that exact approach. See? It's pretty much what we discussed. We initialize a count variable to 0. We get the length of the input list, nums, and store it in n. Then we have two loops nested inside each other. The outer loop runs through I from the start of the list, index 0, up to, but not including, the very last element. The inner loop runs through j, starting from whatever I is plus 1, all the way to the end of the list. This setup automatically ensures that j is always greater than I. Inside the inner loop, that if statement does the heavy lifting. It checks our two conditions. Are the numbers nums and nums equal? And, is the product ij divisible by k? We use the modulo operator % for the divisibility check. If the remainder is 0, it's divisible. If both conditions are true, we increment our count. After the loops finish checking all the pairs, we just return the final count. Let's break that code down just a little bit more. First, we set up our counter, count, starting at 0. We also grab the length of the list, dying, just so we don't have to calculate it repeatedly. Then, this outer for loop starts. Its job is to pick the first element of our potential pair. It iterates through every possible index I, starting from 0 all the way up to n1. So I will be 0, then 1, then 2, and so on. Now, for each value of I that the outer loop picks, this inner loop kicks in. Its purpose is to pick the second element of the pair, j. Notice how it starts from I plus 1. This is key. It guarantees that j will always be strictly greater than I, satisfying our first condition, I less than j. Inside this inner loop is where we perform the checks for the current pair, I, j. First, nums equals nums checks if the values stored at these two positions in the list are the same. Second, ij%k equals 0 checks if the product of the indices I and j is perfectly divisible by k. The Van der Waals means both of these conditions must be true. If they are, we increment our count by 1. Finally, after both loops have completely finished, meaning we've considered every single possible pair, ij, where I comes before j, this last line simply returns the final value of our count. This number represents the total number of pairs that met all the required conditions. So how efficient is this approach? Let's think about time. We have that outer loop running roughly times, where n is the number of elements in the list. And inside it, the inner loop runs, well, it depends on I, but on average it runs about n/2 times. So the total number of checks we do is roughly proportional to n times n/2, which simplifies to n squared. In big O notation, we say the time complexity is order n squared, written as O(n squared). What about memory or space? We're just using a few variables like count, n, I, and j to keep track of things. The amount of extra memory doesn't really grow as the input list gets bigger. So the space complexity is constant, which we call order 1 foot, or O1. Since the problem constraints said n is at most 100, an n squared solution is perfectly acceptable here. Alright, let's quickly recap. The core task was counting specific pairs of indices, I, j, based on 3 rules. I before j, equal values at those indices, and the product ij being divisible by k. The most straightforward way to solve this, especially given the small input size limit, is to use nested loops. The outer loop picks I, the inner loop picks j, starting from I plus 1, and inside we just check the two main conditions, are the numbers equal, and is the product of indices divisible by k. This approach runs in order n squared time, which is perfectly acceptable here, and uses constant extra memory, order 1 foot. Pretty neat. Hope that explanation helped clear things up. If you found this useful, maybe hit the like button, or subscribe for more Leetcode walkthroughs like this. If you still have questions or a different way to think about it, feel free to drop a comment below. And hey, if you're feeling extra supportive, the Boba Fund link is always appreciated. Keep practicing, keep coding, and I'll see you in the next video.